Hi, welcome to this lesson on Euclidean geometry, the Pythagorean theorem. Let's have a look at question 4. So they tell us if chord AQ in this circle with center O, right, cuts BC, which looks like to be the diameter of this line, at the point P at right angles, then explain why triangle ABP is similar to triangle CBA. Okay, so first of all, because we have a circle with a center, that's really important because there's 4 different theorems that we can use when we're talking about centers specifically, and then angles where you're subtending from a center can also be used. Okay, so first of all, I immediately see angles in a semicircle. Because this diameter BC subtends to the point A, automatically that's a right angled triangle. Okay. Then next, we have that since this is a diameter, we can think of radius lines if we want to. So BO is a radius, OC is a radius, that could help us, right? We've also got a chord, but that chord does not subtend anywhere, but it does cut, right? This, the center line cuts the chord perpendicularly. So automatically we know that it bisects that line by a circle theorem result. Okay. So let's go ahead and extract those 2 triangles out and see that they are similar. Okay, most likely going to have to use angle, 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 because we don't know too much information about all the side lengths just yet. Okay, so this is a right angle triangle, and then the other one was ABP, which is this thing here. Okay, there's A, B, and P. And because this is perpendicular, that means that's also a 90-degree angle by angles on a straight line. Okay, so that's 90 degrees. So already we have a common 90-degree angle at angle P and A, which makes sense because angle P and angle A in that sequence need to be equal to each other. So we just need to show one of these other 2 angles are equal. Angle A equals angle C, or angle B equals angle B. All right? And it's quite clear now that if you look at angle B in both of these triangles, they are the same. So therefore, by angles in a triangle, those remaining angles need to be the same. So let's write out our proof for it. Okay, so first of all, we have that angle BAC equals 90 degrees, right? And that again, reason is angles in a semicircle. Okay, and then we also have that angle APB equals 90 degrees because we were given that AP is perpendicular to BC, okay? Cuts at right angles. That's what that means. So therefore, angle BAC is equal to angle APB, right? And that's exactly what we wanted, right? This angle P equals that angle A there. Now, we've also got that in this triangle, that angle ABP equals angle CBA, and that is by common angles equal. Okay, that's this angle B, that's the same in both triangles. Okay, and therefore, by angles in a triangle, we must have that angle BAP equals angle ACB. Okay, angles in a triangle. All right, so therefore we've shown that triangle ABP is similar to triangle CBA by angle, angle, angle. Awesome. Next, they tell us if AB, so this side length here, is square root 6 millimeters long, and PO, this length here, is 2 millimeters long, calculate the radius of the circle. Okay, so essentially if we knew what this length was here, we could essentially add it together to 2 millimeters, and that could help us, right? So let's go ahead and note something. Okay, so look at this big triangle ABC and the triangle ABP. We've just previously proven that those 2 triangles were similar in this order. So I'm going to write that out here. So triangle ABP is similar to triangle CBA. That's what we've just proven. Okay, so now we can use some of that proportionality in that similarity argument there to try and work out the length of the radius. Okay, so what I'm going to take Now, which one of these triangles has a radius length in it? Okay, so the radius length, I think here is BO, right? So for convenience sake, what I'm going to do is I'm going to call the radius length R. So I'm going to say let BO, that radius length, just the same thing as OC or CO, let's call that R. Okay, that's R millimeters long. Okay, so the radius is essentially what we are trying to work out. So I'm going to do the following proportionality. I'm going to look at AB, this one over here, divided by BP. So in the exact same sequence, it's going to be CB divided by AB. Okay, so AB divided by BP is equal to CB over BA. Okay, so CB is this entire diameter length. So that is twice the radius. Okay, so what I'm going to do is I'm going to get CB to be on its own here. So I'm going to cross multiply both sides by BA. So CB equals, well, AB and BA, that's exactly the same length, right? So it's going to be AB squared, and that's still divided by BP. Okay, so now CB I can replace with the fact that it's a diameter, so it's twice the radius, so 2R, and that must equal AB, which we were given as root 6 millimeters, and you're squaring that, divided by BP. So now what is BP? Well, let's think about this. BP is essentially this entire radius length R minus this smaller amount of 2 millimeters. So I can write that as R minus 2. Okay, so here this requires an algebraic setting, being able to assign a variable for the radius and then noting everything down in the circle and the triangle that deals with that radius length. Okay, so now I've got an equation in R that I can solve. So I'm going to multiply both sides by R minus 2. So on the left-hand side is 2R times R minus 2 equals. Now on the numerator here, the square root of 6 all squared is just 6. Okay, now if I distribute that out, I get 2R squared minus 4R. And if I subtract the 6 from both sides, I get minus 6 equals 0. Then carefully dividing by 2, I get R squared minus 2R minus 3 equals 0. And I can factorize that as R minus 3 times R plus 1 equals 0. So therefore, I get two solutions, R equals 3 or R equals negative 1. But again, look at the context of the question. R is a radius length. It doesn't make sense for the radius length to be negative. So we discard that solution and therefore say that R is 3 millimeters long. Okay, so again, to recap here, we use the similarity of the triangles we've just proven. That is a key technique when you're doing Euclidean geometry questions, is that when you ask to prove something is similar or congruent, the next questions usually rely on the fact that you've shown those two triangles were similar or congruent. Okay, and then here we used our algebraic knowledge of assigning the variable R for the radius, right? And then working off the lengths in this proportionality based on the radius length, because that was what we were looking for, the radius. So that's why I paid careful attention to assign it its own variable, so I know what I was solving, instead of just looking at all the assigned letters that were given inside these circles. All right, so again, this is how we would do this type of question. I'll see you in the next one.